In a very real sense, blackbody radiation makes your life possible. The reason you're here, the reason I'm here, we're all here, is because of blackbody radiation. But what is blackbody radiation? A black body is something that emits or absorbs electromagnetic radiation with 100% efficiency at all wavelengths. That means all radiation that strikes the surface of a black body is going to be absorbed. None reflected, it's all absorbed, and it's all re-emitted at a longer wavelength with 100% efficiency. Blackbody radiation is the radiation emitted at a characteristic wavelength that depends on the body's absolute temperature. So the wavelength that is emitted from a black body is going to change depending on that body's temperature. So here we have a laboratory cast iron ball situation. All laboratories face this situation. This cast iron ball at room temperature is going to look like a cold cast iron ball, pretty close to black and cold. As we heat it up using a Bunsen burner, the color is going to begin to change. First, it's going to become dark red. Then it's going to be progressively lighter in red, ultimately orange, then yellow, then blue, then white if it's heated up to that specific temperature. What this means is the brighter you are, the hotter you must be. Here we have a steel heat color chart. Again, as you heat up those cast iron balls, they'll go through this color range. The uncool geeky welders celebrate this, I guess, with this shirt, which is more appropriately turned upside down here. So we go from cold to hot. That can be seen here. This is due to Wien's law. The flux of radiation emitted by a black body reaches its peak value at lambda maximum, which depends inversely on the body's absolute temperature. So what we can see here is a very broad spread of wavelengths at low temperatures. This becomes narrower and narrower, and the wavelength becomes shorter and shorter as temperatures increase. This is something we observe in a hot-rolled steel mill. In the blacksmith world, a blacksmith color chart can be used to estimate the color of steel as it warms up. So again, relatively cold here, just becoming red at around 630 degrees, becoming bright red at 900 degrees, and transitioning into yellow and shorter wavelengths as the temperature continues to increase. If we take a look at this over much more extreme temperatures, at the bottom here we have the temperature chart for the surface temperature of stars. So going from around 1,000 degrees to 12,000 degrees. This is kelvins. Taking a look at our situation relative to the sun, the Earth is emitting radiation with a wavelength of about 10 micrometers, whereas the sun is emitting most of its radiation in the 400 to 700 nanometer range. So if we were to turn the moon off at night, what we would see is a requirement for the sun being sunglasses, the visible range of light here, versus infrared, which we can't see with the human eye. So we would use a starlight scope, some infrared magnifier, so that we can see what's going on at night. And you'll notice if you use these, the very sensitive ones can see the difference in heat given off from a house, from the windows relative to the walls, or a person that's wearing a hat versus not wearing a hat, wearing a coat, not wearing a coat. People being chased through the forest at night can be found using infrared glasses, whereas sunglasses probably wouldn't help you. Mathematically, we can calculate this lambda max as equal to 2898 divided by the temperature in Kelvin. So for the sun, 2898 divided by 5780 kelvins is equivalent to 500 nanometers, which would be in the middle of the visible light range. The Earth, we're going to take a temperature of 288 Kelvin. We're going to divide 2898 by that, and this puts us in the 10 micron range, or infrared radiation. So the Earth doesn't glow. It doesn't appear visible to us without the addition of light. It's not giving off light that we can perceive. And this is related by the Stefan Boltzmann law. In this case, the flux is equal to tau times the temperature to the fourth power. So the Earth is going to receive insolation from the sun. It's going to absorb it completely, 100% efficiency, convert that into a longer wavelength that's going to be dependent on the Earth's surface temperature, which is about 15 degrees centigrade, and then re-radiate that energy back into space at that longer wavelength. According to the Stefan Boltzmann law, again, the flux is equal to the fourth power of the temperature. Many books use the example of a star that's twice as hot as our sun. It's going to release 16 times the energy of our sun because it's twice as hot. Now, some examples in the nighttime sky. We'll pick an easy to find constellation, Orion the Hunter, which looks like an hourglass. The star Rigel has a surface temperature of 11,000 kelvins. Betelgeuse, which is another very easy to find star, has a surface temperature of 3,500 Kelvin. And Sirius, the dog star, the brightest star in the sky, has a surface temperature estimated to be 9,940 kelvins. So 3 different temperatures here and 3 different colored stars. Here we can see Orion as you would see it if you were part of the Hubble telescope. So again, Rigel here, Betelgeuse here. Taking a closer look at them in terms of their relative size and temperatures. Again, Betelgeuse is a bright red big giant at 3,500 Kelvin. Rigel is at 11,000 Kelvin. And the sun is at 5,770 Kelvin here. These temperatures are going to give us the colors. The sun, relatively cool, it's yellow. Betelgeuse, even cooler, red. Rigel, very hot and very blue-white. Sirius, if it was plotted with these stars, would also be very blue-white in appearance. Now, taking a closer look at the size of these, we can see that Rigel is about the size of Jupiter's orbit around the sun, and Betelgeuse is a little bigger than that. It's the size of Jupiter's orbit plus part of Saturn's orbit. And one of the neat things about Betelgeuse is it's getting dimmer. It's gotten about 25% dimmer, I think, over the last 2 years or so. And the implications are Betelgeuse is about 650 light years away from the Earth. It has dimmed by 25%. It's a red giant. It's about to die, and it's going to die in a spectacular way by becoming a supernova. So this may be a supernova about to go off. And when it goes off, it's going to be spectacular. Ultimately, it could destroy all life on Earth. That'll come quite a while after the supernova appears to us in the sky. It'll be the most spectacular thing in the sky, by far. So when we talk about the planetary energy balance, the energy emitted from the Earth must equal the amount of energy striking the Earth from the sun. This is more or less true. But how do we know this? How do we know this to be true? Any difference in this balance would lead to climate change, as the Earth would be losing heat or gaining it. So if our temperature changes, it's because we're keeping more of this incoming heat or giving off more of the incoming heat. Or the amount of incoming heat changes through solar variability. The Earth's surface temperature therefore depends on 3 main things: the solar flux available at the distance of Earth's orbit, the Earth's reflectivity, also called the albedo, that's how much energy gets bounced back without becoming blackbody radiation, and the amount of warming provided by the atmosphere, the greenhouse effect. This is going to be influenced tremendously by blackbody radiation. The effective radiating temperature of the Earth, if there was no atmosphere, can be calculated to be about minus 18 degrees centigrade or 0 degrees Fahrenheit. This is a lot colder than the 15 degrees that we measured today. And this difference is due to the greenhouse effect. The fact that the Earth is habitable is because of the greenhouse effect. The greenhouse effect is natural. It occurs on all planets with atmospheres. It's different from global warming. The greenhouse effect is natural. Global warming is not. The major constituents of the Earth's atmosphere today are listed here. Nitrogen makes up about 78% by volume. Oxygen, about 21% by volume. Argon, about 1% by volume. And water vapor ranges from almost nothing at the South Pole to about 4% in the tropics. Carbon dioxide, a major player in global warming and the greenhouse effect, ranges at around 420 parts per million now. This would be 0.042% by volume. Important greenhouse gases are going to be somewhat different. Water vapor is a big one. It's a very, very effective greenhouse gas. Carbon dioxide, again, is at around 420 parts per million now. Methane is a little bit more than this now. Nitrous oxide, variable, but close to this. Ozone at the surface varies widely due to industry. And Freon, CFCs, in the atmosphere are hopefully still on the way down. Together, these gases act like a greenhouse. Oxygen, nitrogen, and argon will interact with high-frequency, short-wavelength radiation in the upper atmosphere. This is what generates what we call the thermosphere, which should imply that it's hot. It is very hot, but the molecules are so spread out, it wouldn't feel hot. Other than that, the radiation reaches the Earth. It passes through this atmosphere that's relatively clear, except for clouds, and strikes the Earth's surface. Once it strikes the Earth's surface, it becomes blackbody radiation. The Earth's surface absorbs that radiation with 100% efficiency and re-radiates it back into space at a longer wavelength that's determined by the temperature of the Earth's surface, as we saw from Wien's displacement law. So in the greenhouse analogy, energy passes through this glass, heats up the glass a little bit's absorbed here, just like it is in the upper atmosphere. So the glass might be hot to the touch. Beneath that, the radiation continues to the floor of the greenhouse, where it strikes the surface of the Earth in the greenhouse, becoming blackbody radiation, stretching that wavelength out. And now as that radiation bounces off the surface of the floor of the greenhouse, it's a longer wavelength that can't pass through the glass. So the short wavelengths can pass through the glass. Long wavelengths, infrared radiation, cannot. Remember that the Earth emits most of its radiation as infrared radiation. So that's trapped in the greenhouse here. In the atmosphere, it's mostly trapped in the troposphere. So one mind-bending fact is that the atmosphere is actually heated from below. The flux of energy comes from above, but it's converted at the surface, generating infrared radiation, which then heats the atmosphere from below. The oceans are the opposite scenario. The ocean surface is heated directly by the sun. Now, why is the troposphere so unstable? Well, it's because warm air is less dense than cold air, which is why the Remax balloons float over Saskatoon in the summertime. So warm is less dense than cold, and wet is less dense than dry. Water molecules weigh 18 daltons, or 18 atomic mass units, whereas a nitrogen molecule weighs 28, and an oxygen molecule weighs 32. Water weighing 18, being less, makes it more buoyant. Wet air is more buoyant. It wants to rise. Warm air wants to rise as well. So the troposphere is warm, wet air that wants to rise. Eventually it cools as it rises and generates precipitation. And it's this movement that will spill your coffee on an airplane. Now, if the greenhouse effect goes too far, as we can see in cars, if you live in a warm part of the world and you park your car with the windows up, you can melt the inside of your car. Now, this was done with the help of a parabolic mirror, but you can see that commonly temperatures can reach around 200 degrees Fahrenheit, which is around 95 or so degrees centigrade, so very hot. Some people fight this by interfering with blackbody radiation. In this case, you install a reflector in your vehicle. This reflects the incoming radiation back into the atmosphere at approximately the same wavelength as it entered. Because it doesn't act like a blackbody, because it's a reflector, it doesn't generate longer wavelength radiation that's going to heat the interior of the car, so your car doesn't melt. Good things to know.